All right, Chapter 1, Section 6, Complex Numbers. In this section, we're going to look at arithmetic operations on complex numbers, square roots of negative numbers, and complex solutions of quadratic equations. Okay, so if the discriminant of a quadratic equation is negative, the equation has no real solutions. For example, let's consider the equation x squared plus 4 equals to 0. This has no real solutions, right? We could determine that it's got no real solutions in a couple of ways. We could determine that it has no solutions in a couple of ways. If you just look at this for a minute and think about it, in order for this to be true, we would need this part, we would need the answer, the result of this, to be a negative 4. Negative 4 plus 4 equals to 0. But whenever we square something, the output is always positive or 0. It could never be negative. So there's no way to get a true statement out of this, right? That should be pretty easy to see early on. And that's why we needed to invent a new set of numbers, something that would help us answer something like this in some kind of a way. Okay, so if we solve for x squared, we move the plus 4 over to the other side. So we subtract 4 from this side, subtract 4 from this side. We'll end up with x squared equals to negative 4. And now if we proceed with our regular process, we take the square root of this side. We take the square root of that side. Of course, we introduce the plus or minus. And so we end up with this. And again, now we have the situation where we have the square root of a negative number, right? And we know that this is not a real number, right? The answer to this is not a real number. This is what leads to our imaginary solutions. Thus, the negative numbers don't have any real roots. Okay, so to make it possible to solve all quadratic equations, including those, mathematicians invented and expanded a number system called the complex number system. So it all revolves around this issue, that we want to take the square root of a negative number. We want to find a value such that when you square it, the answer is negative 1. There's no such value in the real number system. So we created a new number system. We said, okay, well, let's just assume that it can happen. Let's assume this number does exist. Unfortunately, we called it imaginary, and I think the word imaginary has really kind of made it difficult for people to understand this, because there's a certain resistance to learning a number or a system that's imaginary, because it seems like it has obviously no real connection to reality since it's imaginary. But I think that that's not a fair assessment of it, since a lot of stuff in math is imaginary, right? I know that when we first start, there's a very concrete connection to the real world when we're doing numbers, right? We start counting 1, 2, 3, 4, 1, 2, 3, 4, dot, 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 dot. And we can really see that as a connection to the real world. There's 1 apple, 2 bananas, 3 coconuts. Okay, so there's like real world things associated with these numbers. Even the number 0 was really controversial in its day. How can we have 0? The 0 is the lack of something. There's 0 bananas in my hand. There's 0 apples on that tree. It was controversial in its day, but okay, finally we agreed to it. So I think that that's where we still have this really strong connection to the real world. But where in the real world do we see square root of 2? Right? Conceptually, I know what this is. This is equal to some decimal, equals to some decimal, such that when I square this decimal, the answer is 2. We can get an approximation by using our calculator. But where in the real world is that decimal? Right? So this is already an abstract mathematical idea. Most of math is just an abstract idea, not necessarily connected to the real world. And you wonder, well, why are we even studying it? Well, these concepts in this abstract world often help us understand how the real world works, and helps us understand it and manipulate it and understand it. So back to this specific case, we wanted to figure out some number. We wanted to find some number some number that such that when you square it, the answer was -1. That's what we wanted to find. There's no such number within the real number set, so we just said, well, let's just create it. Let's just pretend that it exists. In this abstract mathematical world, it'll exist. We will call it an I or an imaginary value. It's the number such that this is true. And if we just momentarily pretend that this number exists, it'll help us answer questions that ultimately help us to solve real-world situations and help us get a better understanding of the world around us, right? So, say rocket science, we ran into some problems. There were some equations that we needed to solve, and in order to solve them, we ran into this problem about an even, something like the square root of a negative number kind of a situation. So we go around it. It's kind of a roadblock. You go into this imaginary field, and you work within that field, and then eventually, not always, but often you get back into the real number set, and you're able to find a real solution, or at least a really good approximation, an approximation that's good enough to help us achieve whatever we're doing. Okay, so hopefully I've convinced you a little bit that even though it's called an imaginary number, it is important. It's valid, it's useful, and it's a big part of math. So we just have to accept that this is true. We are going to define it. We're going to define this new number I, which is exactly this thing. It's I is equal to the square root of -1, which means then, by definition, that when we square both sides, I squared equals -1. Here it is. This is that number such that if you square it, the answer is -1. Okay, so once we've accepted that that's true, then we can combine it in this form to create a whole new number system called the complex numbers. The complex numbers are going to be numbers that are written in this form. It is A plus BI, where A and B are real numbers, and of course I is this guy. In math, I is almost never used. I guess it's often used as an index counter in certain situations, but other than that, we try to avoid the variable I as much as possible to reduce confusion. So most of the time when you see an I, it's going to be this, an imaginary number. We should have just used it once and retired it, but we do use it as an index often, as a counting index, especially with like Riemann sums. Okay, so a complex number is an expression of the form A plus BI, where A and B are real numbers, and I squared equals -1. The real part of the complex number is the A out in front, and the imaginary part is the B. Two complex numbers are equal if and only if the real parts are equal and their imaginary part is equal. Okay, so when you're given a complex number, the number out here in front is the real part, and then the imaginary part is the B, right? Just the B, not the BI, just the B. The B is the imaginary part of your complex number. So for example, just to write down some quick little examples of things that fit this form, we could have the complex number 3 plus 2i. Then the real part's a 3, the imaginary part's a 2. Good. It could be 3/4 minus 5/8 I. In this case, of course, we know that we have to rewrite it as an addition. So this would then be rewritten as 3/4 plus -5/8 I. And now we have that the 3/4 is the real part and the -5/8 is the imaginary part of our complex number. Keep in mind that we can also have a 0 for one of these. So for example, we could have 0 plus 9i, and then of course the 0 doesn't really do anything, so this just translates to 9i. Good. Okay, so if you just see 9i, then it is a complex number, and the a, the real part, is 0, and the imaginary part is the 9. So the real part is a 0, and the imaginary part is the 9. Okay, so if you just see the I by itself, then we can rewrite it as 0 plus 1 times I, and so the real part is 0, and the imaginary part is a 1. Likewise, if we just see a whole number like this, 5, it is a complex number. The number 5 is the same thing as 5 plus 0i. Okay, so the real part is a 5, and the imaginary part is a 0. So this means that every single real number is actually a member of the complex number set. It's just that all the real numbers are complex numbers where the imaginary part is a 0. Right? It's kind of like when we first learned about fractions, right? We had our counting numbers, right? We first learned to count 1, 2, 3, dot, 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 dot. Then later we learned about 0. Okay, so then we learned 0, 1, 2, 3, right? So the counting numbers, these are called the whole numbers because we threw 0 in there. Then we got integers. Then we learned about integers. -1, -2, -3, dot, 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 dot. Then 0, then 1, then 2, then 3, dot, 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 dot. And then we learned about fractions. When we learned about fractions, maybe we learned about 1/3, and we learned about 2/5. But then we realized that if you just have a whole number, we can always just stick a little 1 underneath it, and it's a fraction. So really, all of these guys are fractions. They're just a simple fraction where the denominator is a 1. Right? So that's what we learn here. We've actually been working with the complex numbers the entire time. Every single real number is a complex number. It's just that it has a plus 0i at the end of it. Right? It's not just 3. It's really 3 plus 0i. It's not just 3.25. It's 3.25 plus 0i. Right? We can always attach a 0i behind any real number, and you got yourself a complex number. So we've been working with complex numbers this entire time. We've just been working with the easy ones. Now we want to learn how to work with the more complicated ones, the cases where the imaginary part is not 0. Okay, so here's some examples, some more examples of complex numbers. So we have 3 plus 4i. The real part's a 3, the imaginary part's a 4. We got 1/2 minus 2/3 I. The real part's a half. The imaginary part is -2/3. We got the number 6i. The real part is 0. The imaginary part is 6. -7. The real part is -7. The imaginary part is 0. Okay, how do we do arithmetic with complex numbers? Complex numbers are added, subtracted, multiplied, divided, just as we would any number of the form a plus b root c. Okay, so we're going to have to go back to our rules with binomials to see what this is. The only added element to this is that we know that whenever we have I squared, we'll get -1. Okay, so let's expand a little bit on that. So we know, of course, that by definition, I is, of course, equal to the square root of -1. And if we square both sides, we're going to get I squared is then equal to -1, right? That's by definition. What happens if we have I cubed? I cubed is equal to I squared times I to the first power, right? They have the same base. We just add the exponents. That would give us that 3. And then, of course, we know that I squared is -1. So we get -1 times I, or just -I, right? So we have I cubed is equal to -I. What about I to the 4th power? I to the 4th power is equal to I squared times I squared. And we know that each one of these I squares is a -1. So we get -1 times -1, which equals to +1. So I to the fourth power equals to positive 1. Okay, so nice little pattern. I is just I, so we just have I. And then I squared is negative 1. I to the third power is negative I. And I to the fourth power is positive 1. So here, let me so I'm just putting I equals I. There's nothing special about that. So I is just I squared is negative 1, I to the third power is negative I, and I to the fourth power is 1. We'll continue with this pattern down the road a little bit, but for now, that's more than enough for what we wanted to do. Okay, so here is a complex number times a complex number. We have a plus bi times c plus di. This is where the real part of this imaginary number is the a. The imaginary part of this complex number is a b. And then here, this is the real part of this complex number, and this is the imaginary part, right? So let me highlight all the real parts. This is the real part, and this is the real part. And then over here, this b is the imaginary part of the first complex number, and the d is the imaginary part of the second complex number. How do we multiply these? Well, good old FOIL will work out. So the first, the outer, the inner, the last, or that red claw, that will do it. Okay, so this will be equal to a times c plus a times di, a di, plus c di, I'm sorry, cbi, that would be this one, and then finally dbi plus bdi. Right, this is the F, the O, the I, and the L. So this is the F, the O, the I, and the L. FOIL. Okay, so next we're going to combine like terms. So that means that this term and this term are like terms. Oops, I forgot the squared. It's the last, the L is bi, di, so this guy gets squared. bdi squared. Okay, so combine these two as like terms and replace this guy by a negative 1. So this is equal to negative 1. Cross that out. Okay, so I'll end up with AC plus, now I'm going to factor out this I, and we end up with AD plus CB I. And then we end up with a minus dBd. Good. So I'm going to combine these two, and so I'll end up with AC minus BD plus parentheses AD plus CBI. And so if we think of this as one little thing over here, this is the number AC minus BD. Right? Once you gave me the specific values of A, B, C, and D, I know that I can calculate what this is, plus then I can calculate what this is, and my final answer is going to be a real number as well, where the final answer is going to be here. Whatever this calculates to, this is going to be the real part of my complex number, and whatever this calculates to will be the imaginary part of my complex number, right? Real part plus real part I, right? It'll fit the same form of a complex number. Right, and that's captured in this little blue box. Let's zoom in a little more. So if we have one imaginary number plus another imaginary number, this is how we add them. We add the two real parts, combine like terms, and then bring together the two imaginary parts, factor out the I, and we end up with this. So here is the new solution, and again, notice that the final answer is an imaginary, it's a complex number, where this is going to be the real part of my complex number, and this is going to be the imaginary part of my complex number, right? And so we got it by adding the two real parts together and adding the two imaginary parts together. Good. Similar with subtraction, we just have to keep track of that subtraction symbol. So it's distribute, combine again the real parts, we'll end up with a minus c. So this will be, once you give me the values of a, b, c, and d, I can calculate what this is, and that'll be the real part of my complex number. And then I distribute this guy, combine like terms, factor out that I, and we'll get that this and this give me the imaginary part of my complex answer. Good. Okay, and now this is the one we calculated. We distribute, FOIL, combine like terms, and we see that this ends up being the real part of my complex number solution. And then this, whatever this calculates to, ends up being the imaginary part of my complex number solution. Okay, let's do some examples. Let's do this one. So again, just to really highlight, this is the real number part of my complex number. This is the real number, the real part of this complex number. This is the imaginary part of my complex number. And this minus 2 is the imaginary part of this complex number, right? So I do definitely have one complex number plus another complex number, the summation of two complex numbers. Get rid of that. So how do we do this? We don't need to FOIL. Foiling is for multiplication. All we have to do is add it up, right? So technically, let's do this one. Oops. Technically, we'll do it this way just one time, just to make sure it's clear. Technically, what's happening is that there is one copy of this complex number, so there's really this imaginary 1 there, and one copy of this one, there's an imaginary 1 there, which we can distribute. So we end up with 1 times 3, well, that's just going to be 3, plus 1 times 5a, well, that's just going to be 5i, plus 1 times 4, well, that's just 4, and 1 times negative, so an addition of negative 2i, or we can leave it as a subtraction of 1 times 2i, which is just going to be 2i. Okay, so when there's just an invisible 1 there, these parentheses don't really do anything, right? We can just get rid of them. So most people just kind of skip this step here. It's not really necessary, and that's perfectly okay. Just want to make sure it was clear why we were just getting rid of it. So why do we include it in the first place? Well, it's just to really clarify that this is one complex number plus another complex number. Okay, combining like terms, we get that we can add the 3 and the, combine them, it'll be the 3 plus the 4 plus 5i minus 2i. Then we can, just to put it in that form, I'm going to do this, 3 plus 4 plus, and then 5 minus 2i, and now I have the form I want, right? So note that this is the a from here. If we had a plus bi plus c plus di, note that in this little example, that would mean that this is the 3 and this is the 5, and this is the 4, and the d is negative 2. Okay, so doing that, we can see that the formula is to add the real part, so it'll be the 3 plus the 4, right? This is the A plus the C, plus, and then the 5 is the B plus the D, I, from there and there. Okay, so it fits that form from above. If you want to just kind of follow the this guidance. a plus c plus b plus d. Okay, so it fits that form, and then we can just go ahead and simplify it by doing the arithmetic. This is 7 plus 3i, right? A complex number solution, where this is the real part and 3 is the imaginary part. Okay, so adding complex numbers, very easy. So here's the solution the author had. How about subtracting complex numbers? Super easy as well. We're not going to do as much detail this time. I think it's pretty obvious. We just have to distribute this guy. So make sure you distribute that -1 into each one of these terms. And we'll end up with 3 plus 5i minus 4 plus 2i. Combining the like terms, we end up with 3 minus 4 plus 5i plus 2i, which will then give me -1 plus 7i. Right? Again, this is going to be the real part of my complex number solution, and this is the imaginary part of my complex number solution. Okay. -1, 7i is what the author did, same thing. Okay, now multiplication gets a little more complicated, but not much. Just keep in mind that as you're doing this to combine like terms, and of course we're going to use that I squared equals -1. Right? Whenever you run into I squared, you can replace it as a -1. So that creates a way for us to eliminate the i's. Right? Whenever we can get to a point where we have an I squared, then that turns into a -1. So this is a transition back into the real numbers as we know them. Okay, so we're going to have to FOIL this guy. FOIL and FOIL. FOIL and FOIL. Okay, so this is going to be equal to 3 times 4 plus or minus 3 times 2i plus 4 times 5i minus 2i times 5i. Right, so that's the FOIL, FOIL. And so that simplifies to 12 minus 6i plus 20i minus 10i squared, which we know is just going to be a -1. So this simplifies to 12. Combining these two together, -6 plus 20 gives me the plus 14i. And then we end up with a minus, and then 10 times -1, which is going to become -10. And then a subtraction of a -10 is going to become a positive. So we get 12 plus 14i plus 10, and then we bring together the 12 and the 10 to give us 22 plus 14i. That's our final answer. So the multiplication of two complex numbers gives us another complex number where the real part is 22 and the imaginary part is 14. And 14i. Okay, express I to the power of 23 in the form of a plus bi. Okay, so let's look at a pattern with i's. I started up above, so let's keep going with that pattern. So we have I is just I, nothing special about I. And we saw that I squared was equal to -1. And we saw that I to the third power was equal to I to the second power times I to the first power, which gives you, that looks like a negative, which gives you -1 times I, or just -I. Then I to the fourth power is equal to I squared times I squared. And then that gives you -1 times -1, -1 times -1, which gives you +1. Okay, so we have a nice little pattern for the first 4, and then once you go past the 4, so you get to 5, then 6, then 7, what we want to use is this guy right here. We want to use the fact that I to the 4th power equals to 1. Once we do that, then we can separate any higher power into little groups that have 4s in it, as many 4s as you can get in there, so that all those turn into a 1. So for instance, I to the 4th power is going to be, I to the 5th power is going to be I to the 4th power times I to the 1st power, and then that I to the 4th power becomes a 1. So we get 1 times I, or just I. So I to the 5th power is just I. Now I to the 6th power, that's going to be I to the 4th power times I to the 2nd power, right? And then this I just becomes 1, and I squared becomes negative 1. So I to the 6th power is going to become 1 times negative 1, which equals just negative 1. Okay. Let's keep going a little bit. How about if I had like I to the 14th power, like that. Okay, what we want to do is think about how many times we can separate this into powers of 4. So this is going to be I to the 4th power times I to the 4th power. I've taken care of 8 of them already. I can do one more. I to the 4th power, that's 12, times I to the 2nd power. Right? We know from our properties of exponential numbers that if we have the same base and we're multiplying them, we add the exponents. So this is 4 plus 4 plus 4, that makes it 12, plus 2 makes it 14. And the reason we do this is because all of these turn out to be 1. I to the 4th is a 1. I to the 4th is a 1. I to the 4th is a 1. And then something else. Now in this case, it's I to the 2nd, which happens to be negative 1. So I to the 14th power is equal to 1 times 1 times 1 times negative 1, which then just equals to negative 1. So I to the 14th is negative 1. Let's try another one. How about if it was more complicated, something like, well, how about the I to the 24th? I'm sorry, 23rd. I to the 23rd power. Well, we'd want to do I to the 4th, I to the 4th power, times I to the 4th power, that's 8, that's 12, that's 16, that's 20. And there's still 3 more. I to the 3rd power, right? So all these powers of I to the 4th become 1. I to the 4th becomes 1, I to the 4th becomes 1, I to the 4th becomes 1, I to the 4th becomes 1. And this I to the 3rd power, we saw from up here that I to the 3rd power is really just negative I. So this guy just becomes negative I. So we end up with a 1 times 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 a negative I. So the whole thing is just going to be negative I. And that's our answer here, negative I. Good. So what we could do, though, is come up with better notation than this. Let me come over here. So one way to represent the same idea is to say that this equals to I to the 4th, and then identify how many copies of that we had. So there was 1, 2, 3, 4, 5 of them. So I to the 4th times 5. And then there was the extra, so then times I to the 3rd power. Or another way of saying this is that it's I to the power of, and then this is going to be equal to 4 times 5 plus 3. Okay. Either way. So we want to be able to rewrite any number they give us into something of this form, and it's really going to be that extra constant out here which tells us what our final result is going to be, right? This extra constant out here is either going to be a 0, meaning that we had an even number of copies of I to the 4th, multiples of I to the 4th, or it's going to be a 1, or a 2, or a 3. It can't be a 4, because if it was a 4, then we'd have one more copy, right? If I had I to the 24th, then I can rewrite this as I to the 4th 6 times, and then there's nothing remaining. So then, times I to the 0. And so this becomes 1 times 1. The whole thing just equals to 1. I to the 24th is a 1. I to the 25th is I to the 4th times 6, and that takes care of 24 of them, and then there's one more, times I to the 1st, right? I know that this is going to become 1 to the power of 6, times I to the 1st power, which just becomes I. Okay, so hopefully that pattern is clear now. So I to the 23rd is equal to I to the 4th raised to the power of 5 times I to the 3rd power, which then becomes 1 to the 5th power times I to the 3rd power. And we know from up here that I to the 3rd power is just negative I. So this becomes negative I. And we can expand this by noting that this is a complex number where the real part is 0. So this is equal to 0 plus negative 1 times I. And now we've put it into exactly this form. The role of A is being played by a 0. The role of B is being played by a negative 1. So it's a complex number where A equals to 0. It's a complex number where the role of A is being played by a 0, and the role of B is being played by a negative 1. The imaginary part is negative 1. Okay, so that's how the author wrote this. Let's do one more just for fun. What if it was I to the power of 87? Like, what is I to the power of 87? Okay, so your first goal is to determine how many multiples of 4, even multiples of 4, can fit, can be brought together, can be brought together out of 87, right? So if you have 87 i's, how many groups of size 4 can you form, right? So if I wanted to say 10 of them, 10 times 4 is 40. So 10 little groups of I to the 4th would get you to 40. So more than that. How about 20 would be double. 20 times 4 is 80. So we're getting closer. So 20 would be 80, 21 would be 84. So 21 times 4, that takes care of 84 of these i's, right? So this 21 means that there are 21 little groupings of little groups of I to the 4th, right? So 4 i's are kind of corralled together, and I do that because I know that that's going to end up being a 1. Okay, and then what's remaining is this I to the power of 3, right? Because this takes care of 84 of them, there's still 3 remaining. Now this equals to that. And so this I to the 4th power, this equals to a 1. So we have 1 to the power of 21 times I to the power of 3. I to the power of 21 is just going to be equal to 1. So that's just going to be 1 times I to the 3rd power. And as we already saw, I to the 3rd power is just equal to negative I. So I to the 87th power is really just equal to negative I. And if I wanted to write it in that complex number form, just to be super solidly clear on what it is, we have I to the 87th power is equal to 0 plus negative 1I, right? Where 0 is the real part of the complex number and negative 1 is the imaginary part of the complex number. Okay, so that should be super clear by now, I think. Okay, well, how do we do division? Division of complex numbers. This one's a little bit trickier, but not that bad. So for the complex number z equals to a plus bi, we define the complex conjugate. We've seen this word before, the conjugate. So now we have the complex conjugate, z bar. So it's just a common notation to reference its complex conjugate by putting a little bar over that, so that z times z bar is the multiplication of the z number, this one, times its conjugate, which is this one. And you'll see that when we FOIL this out, something great happens. The middle terms cancel out, as we've seen before, and we end up with just this, right? So let me FOIL those out to see how this is determined. So if we have a plus bi times a minus bi, right, and then we proceed to FOIL these. This times this times that, this times this, and this times that. We end up with a squared for the f, and then minus abi from there, the last two, and then the inside two become plus abi, the inside two, minus, and then the last two, minus bi times another copy of bi. Okay, so simplifying this, we get a squared. Now notice the middle two terms cancel out. They're identical. Minus abi plus abi. So these guys completely cancel. And what we have left over is a minus bi. So we end up with a b squared I squared. Right? bi times bi gives you a b squared I squared. And of course, we know that I squared equals to -1. So we end up with a squared plus -1 times b squared. And then addition of, oops. Jumped the gun here. So this comes from there. And then this -1 comes from there. And so we end up with a squared plus b squared. So what we should get out of this, the important thing we should get out of this, is that when we have a complex number and then we multiply by its complex conjugate, the output is going to be a number that doesn't have an imaginary part, where the imaginary part is 0, right? The i's are gone. So we can always put a plus 0i at the end, and it is a complex number, so I'm not going to say it's not a complex number. It's just that the imaginary part of the complex number is going to be 0, right? So the product of a complex number and its conjugate is always a non-negative real number. A non-negative, that's another part of this. Since this squared plus this squared, this is going to be some non-negative value, right? Okay, so let's see how that's useful. When we want to divide two complex numbers, say, for example, a plus bi divided by c plus di, this is a division of two complex numbers. Multiply the numerator and denominator by the complex conjugate of the denominator. That's going to guarantee that the denominator is going to be a non-negative complex number where the imaginary part is 0. The I is going to be gone in the denominator. Now, the numerator might end up being something a little more complicated, but it will simplify in the numerator to be some form of a complex number. And then you'll be able to break up the final result into two different fractions such that we have a number written again in complex form. Right? In other words, to finish this thought, this is going to be some number we can calculate with no I in it. Right? So once they give us the A, B, C, and D, we'll be able to calculate this out. This is just some number. So we'll be able to separate this into two fractions. One of it will be AC plus BD divided by C squared plus D squared plus, and then this one will be BC minus AD divided by C squared plus D squared I. And so we'll be able to rewrite this once the numbers A, B, C, D are provided. This is just something to calculate, right? This is just arithmetic. We'll be able to calculate it, and whatever that number is, that'll be the real number, the real part of my complex number solution. And when I get the numbers A, B, C, D given, then I'll be able to calculate this part out there, and this number, whatever it calculates to, will be the imaginary part of my complex number solution. So the division of two complex numbers is going to give me a complex number, and to find it, all I have to do is multiply the numerator and denominator by the complex conjugate of the denominator. All right, let's do an example. So here's an example. I have 3 plus 5i divided by 1 minus 2i, a complex number divided by another complex number. So following the suggestion, the way to figure out what this is I'm going to multiply the numerator and denominator by 1, right? A new form of 1. Except that in this case, the version of 1 that I want is going to be the complex conjugate of the denominator. So I'm going to multiply the numerator by 1 plus 2i, multiply the denominator by 1 plus 2i. Good. So then we're going to have to FOIL our hearts out here. FOIL. We'll end up with 3 plus 5i times 1 plus 2i. So we're going to have to multiply this times this times that, this times this, and this times that. And that's just in the numerator. In the denominator, I'll have a 1 minus 2i times a 1 plus 2i. And again, we're going to have to FOIL. So first, outer, inner, last. So I'll have a giant fraction, where in the numerator I'll have 3 plus 6i plus 6i plus 5i plus 10i squared. We'll simplify that in a little bit. In the denominator, I'll end up with a 1 plus 2i minus 2i minus 2 squared, I'll just say 4, minus 4i squared. Right, each one of these squares, I squares, becomes a negative 1. Negative 1 there, negative 1 there. And so we can simplify this to be a giant fraction where we have a 3 plus 11i, combining the 6i and the 5i, plus 10 times negative 1. In the denominator, we end up with a 1, and then this is the great part. These guys cancel. 2i minus 2i, those guys cancel. And then I'll have a minus negative 4, which gives you plus 4. So in the numerator, I get 3 plus 11i minus 10 divided by 1 plus 4, which equals to negative 7 plus 11i in the numerator, combining the 3 minus 10, that gives you negative 7, divided by 5. And now we can separate this into 7 over 5 plus 11 over 5i. And that's my final answer. So this is my complex number solution. A complex number divided by another complex number gives you a complex number, where this is the real part of my complex number, and this is the imaginary part of my complex number, right? The 11 over 5. Okay, moving on. Let's see what the author did. And matches, yeah, same thing. Okay, another example. Express the following in the form of a plus bi. All right, so remember that 4 remember that 4i is the same thing as 0 plus 4i. So if this is my complex number z, then its complex conjugate is going to be equal to 0 minus 4i, or just negative 4i. All right, so following that advice, in order to simplify this, I'm going to multiply the numerator and denominator by minus 4i, all over minus 4i. And so we end up getting 7 times negative 4i plus 3i times negative 4i divided by negative 4 squared, or just 16, and then I squared. Right? So we'll get negative 28i minus 12i squared divided by negative 16i squared. And then each one of these I squares can become a negative 1, negative 1, negative 1. And so this simplifies to negative 28i minus negative 12 divided by negative 16 times negative 1. So this then turns into negative 28i plus 12 divided by positive 16. And so just moving things around a little bit, I end up with 12 divided by 16 plus negative 28i divided by 16, which can then reduce. 4 goes into 16 4 times. 4 goes into 12 3. So this is going to be 3/4 plus 7 4. 4 goes into 28 7 times. So this is negative 7/4 I. So there we go. There's our final answer, where this is the real part and this is the imaginary part of my complex number. Okay, square roots of negative numbers. So just as every positive real number r has two square roots, square root of r and negative square root of r, every negative number has two roots as well. So what is this talking about here? Remember that if we have blank squared, that's like x squared equals to 16. Blank squared equals to 16. Well, by just looking at that, we know there's two possible answers, right? Of course, we can put in a 4, or we can put in a negative 4. There's two possible answers to this. When we solved it, right, if we had the r squared equals to 16, and then we took the square root of both sides. Let's take the square root of this, square root of that. We have to introduce the plus or the minus. And so we end up with x equals to plus or minus root 16. Obviously, root 16 is just 4, so then we would just say that x equals to plus or minus 4. But that's just because this happened to be a nice perfect square. This process works even if we don't have that. So if we have x squared, something squared equals to 3, for example, we would still do the same thing, and we'd end up with x equals to plus or minus the square root of 3. Right? And we would just leave it like that, unless you want to use your calculator to turn it into a decimal approximation. But this is good enough, right? This symbol is referring to some decimal out there that we know exists, at least in an abstract math sort of way it exists. And this decimal has the property that when you square that decimal, the answer is 3. Right? So that's what this is talking about, that every positive real number r has two square roots, either square root of r or negative square root of r. So if x squared equals to r, we take the square root of both sides, and so x equals to plus or minus the square root of r. Okay, so that's true as long as we insert r as some value that is non-negative, right, within the real number set. But what if it was negative, right? What if it was negative? If negative r is a non-negative number, then its square roots are plus or minus I root r, because I square root of r squared equals to I squared times r, which equals to negative r, and negative I square root of r squared equals to negative 1 squared I squared r, which equals to negative r. What in the world is all that saying? Well, just like as up here, right, kind of like up here, I just convinced you that, well, look, you can put in a 4 or you can put in a negative 4, and then the answer works. We can do the same thing here. So if we had some statement of r equals to, x squared equals to negative r, so that means that r itself is non-negative. let's just for a minute assume that R itself is something that's definitely positive, 0 or positive. Then that means, well, let's make it strictly greater than 0. Strictly greater than 0. Then that means that negative R is going to be negative. Negative R is less than 0. Negative R is a negative number. Okay, so if we have this, then we go through our process, and we're going to say that we're going to take the square root of both sides. Square root of this side, square root of that side. That gives you a plus or minus on this side. And once we do that, okay, we have a minus 1 there. What we're going to do is we're going to say that that is equal to I. Pull out that I because, well, okay, let me take another step here. This is going to be plus or minus square root of negative 1 times R. And we know that the square root of negative 1 is R, so we're going to say x equals to plus or minus I square root of R. Okay, so both of these things work because if we replace this x by either one of these, we're going to get a true statement, right? Check. Blank squared equals to negative R. One thing we could do is insert an I root R, right? Let's check it. I root R squared, well, that's going to be equal to I squared times the square root of R squared. And we know that, oh, let's put it this way. We know that I squared, well, that's just negative 1, times the square root of R squared, well, that's just negative R. So this equals to negative R. So it works out. And we also know that negative I square root of R also works. Right? So let's try it. Let's check it. If we tried negative I root R squared, and we try squaring it, of course, we're going to get a negative 1 squared, and then we're going to get an I squared. Right? Each one of these little components, each one of those gets squared. And then we get a negative R, I'm sorry, square root of R squared. And so this becomes positive 1. And then I squared, that becomes negative 1. And then this becomes R. So 1 times negative 1 times R is going to give you negative R. Okay, so we've just shown that in either case, both of these give you a true statement. This one and this one are two values that can be inserted into this little statement to make it a true statement. Right? Just like up here when we did the 4 and the negative 4, they gave you a true statement. Here we're showing that either one of these two gives you a true statement. Right? That's what this is. What this was stating up here. What's the point of all this? Okay, well, this is just giving us a way to deal with the square root of a negative number. So if negative R is negative, then the principal square root of negative R is the square root of negative R equals to I root R. Okay? The two square roots of negative R are I square root of R and negative I square root of R. So we usually write I root B instead of the square root of BI to avoid the confusion. Right? So in other words, usually we like to write the variable behind the number. So if we have 3x, we like to see it that way. It's technically allowed to have x3, same thing, they equal each other, but this just looks weird, right? We're used to seeing the number first and then the letter. However, in this situation, if we have square root of 2i, right, clearly the I is outside the root. But this often gets confused with the other case where we could have this, right? And they don't equal each other, but notation-wise, writing-wise, this gets confused with this all the time, and these do not equal each other. So in order to avoid this confusion, we've adopted the idea that just in this case, we like to stick the I out in front. I root 2, right? Which is kind of like this. You're putting the letter in front and then the number, but it really helps with confusion. So that's what this is saying. We're used to putting the I in front of the number just in the case of complex numbers for this reason. Okay, but what does this really do? This helps us deal with a negative inside a root. Whenever you see a negative inside an even root, a square root, we're going to separate it into a negative times r, where r is the positive, right? So then we have a negative there. And then we can just rewrite it using this property as I square root of r. So here's some quick examples. Here we have the square root of a -1. Well, this one is just obvious that this is just equal to I. Nothing special needs to happen there. It's by definition what it is. Okay, in this case, we want to say that because there's a minus in there, minus times 16, that this is equal to I square root of 16. Right? The first thing you should do is deal with the fact that there's a negative in there by doing this before you do any other arithmetic. We'll see an example of that in a second. And then you can conclude that this must be I times 4. And then in this case, we do switch it around since there's no possibility of making a mistake as 4I. Right? It was just in this case that we don't want to switch it around because instead of I root 16, if somebody wrote this, it might look confusing and someone might say, are you trying to say that? Careful not to do that. That's why we stick the I out in front. Okay, and in this case, this is just going to be equal to I root 3, and then there's nothing else you could do beyond that, right? It doesn't simplify any further. In all of these cases, technically we have a 0 for the real part of the complex number, so you can also write it as 0 plus root 3, and then make it really clear that the I is not inside the root, and this is just to put it in the form a plus bi, just to really clear up that this is the real parts and this is the imaginary parts of our complex number. Okay, I think that should be pretty easy. Moving on. So special care must be taken in performing calculations that involve square roots of negatives, because although the square root of a times the square root of b is equal to the square root of a times b when a and b are positives, this is not true when both are negative. So here is an example of why that is. I don't know why it's way down there. So note that if someone treats this question this way, do I have room here? Okay. So note that if someone treats this one this way and says, I know the square root of -3 times -2, and then that equals to the square root of negative times negative, that's a positive, that's going to be 6. And so they get that the square root of -3 times the square root of -2 equals to the square root of 6. That is the wrong answer. Right? The real answer should be this. We have square root of -3 times the square root of -2. So the first thing you should do is deal with the fact that you have the square root of a negative. So we have to change this to an I root 3 times an I root 2. So now we can combine these guys together. So I end up with I times root 3 times root 2. I'm just moving them around, which gives me an I squared times the square root of, and now we're allowed to do this. This is 3 times 2 since they have the same index. And so now this is equal to -1 times root 6. So the real answer is this one. This is the real answer. This is correct. This is wrong. Right? So it's just a simple little example that shows you why you can go down the wrong path if you start doing arithmetic with the roots when you're dealing with a negative inside the root. So the first thing you should do is deal with the fact that there's a negative inside the root. You got to deal with this thing, first thing, right out of the bat, and rewrite it with an I outside, and then you can deal with it. Then you can proceed to simplify the problem. Okay, keep that in mind. So complex solutions of quadratic equations. So We've already seen that if a does not equal 0, then the solution to a quadratic equation is going to be ax squared plus bx plus c equals to 0. And so we have the quadratic formula. Remember, we derived this very painfully by doing the whole complete the square process. And then once we found this quadratic formula, we also pointed out that if we focus on this part, the argument inside the root, if this part is negative, then we would end up with an imaginary number. And in the previous section, we kind of gave up there and said, oh, well, there's no real number solutions. But now that we have, now that we're armed with this new number system, the complex numbers, now we see that we do have a solution. So in fact, any quadratic equation has solutions as long as we're allowed to go into the complex numbers. Right? There's no such thing as no solution. All quadratic equations have solutions. It's just that some of them might be in the complex number. Well, everything's in the complex number. It might have an answer that has an imaginary component. So here's an example. Solve this this equation. All right. Well, this one's easy. So let's solve it this way. We have x squared plus 9 equals to 0. We could use the whole quadratic formula thing, and that would be this way. That would be a, let's put a 0x plus a 9 equals to 0. So this fits the form of ax squared plus bx plus c equals to 0. And that's where the role of a is being played by a 1. The role of b is being played by a 0, and the role of c is being played by a 9. And so now we can go over to our quadratic formula and say that x equals to negative b plus or minus the square root of b squared minus 4ac all over 2a. And now it's just a simple plug and chug, right? The b is a 0, the b is a 0. So this is going to be equal to plus or minus the square root of negative 4. Let's just put it in there, make sure people see where that's coming from. This is going to be negative 0, so negative 0, and then 0 squared minus 4 times something all over 2 times something. So B was a 0, the A is a 1, the C is a 9, and then 2 times 1. Okay, so then you can simplify this whole process, and we end up with just negative 0 is just 0, so we end up with plus or minus the square root of 0 squared is 0, minus 36, so minus 36, and the whole thing gets divided by 2. And then we deal with that minus in there by pulling out an I, and so we end up with plus or minus I times square root of 36 all over 2, and square root of 36 is just going to be 6. So after all that work, we see that this is really just going to be plus or minus 3i. All right, well, that was way too much work. This is a really simple one, so we could just do it this way instead. Equals to 0. Let's subtract 9, minus 9, minus 9. And so we end up with x squared equals to negative 9. Now we can do our square root on both sides. Take the square root of this side, plus or minus the square root of that side. And we're allowed to do that. So we get x equals to plus or minus square root of negative 9. And then the way we deal with that minus is to bring out an I. So we get that x equals to plus or minus I root 9, which then gives you x equals to plus or minus I times 3, or x equals to plus or minus 3i. Same answer as before. Same answer as this one. Right? And that's because 2 goes into 6 3 times. Right? Maybe I should have put that extra little step here. This is plus or minus 6i divided by 2, and so the 6 and the 2 reduce to give you a 3. Okay, so now let's check our work. Let's make sure that these are in fact good solutions. Check. So blank squared plus 9 must be 0. And so we think one of those answers is to put a 3i in here. 3i goes right in there. So what are we going to get? We're going to end up getting 3i parentheses squared plus 9 equals 0, which gives me a 9 times I squared plus 9 equals to 0. I squared is negative 1, so we get negative 9 plus 9 equals to 0. That works out. Right? And that's because this I squared equals negative 1. Okay? Or the other one we could do is we can plug in a negative 3i. Negative 3i can go in there. Let's check to make sure that that also works out. We end up with negative 3i squared plus 9 equals to 0. So we get negative 3 squared I squared plus 9 equals to 0. So that gives you a positive 9 times a negative 1 plus a 9 equals to 0. So negative 9 plus 9 equals 0. It worked out. Good. So we've confirmed that both of these do work. They do solve that equation. You have the option of using the quadratic formula, but I think in these kinds of cases, this is much simpler, right? So if you just have the variable squared plus or minus a constant, right, then it's just easier to solve for that variable squared, get that by itself on one side, equals to the rest that doesn't have an x in there, so constants on the other side, and then take the square root of both sides. Don't forget that plus and minus to get both the solutions. Okay, so that's how the author solved it. Move the 9 to the other side, take the square root, and then you get both solutions. What about something like this? Well, this one's a little bit more complicated since we have a term that has an x squared and a term that has an x. I can't solve it like before. I can't isolate the x squared, take the square root of both sides. So in something like this, maybe it is a little easier to figure out how to find the quadratic formula for it, right? So this fits the form ax squared plus bx plus c, where the role of a is being played by a 1, the role of b is being played by a 4, and the role of c is being played by a 5. Good. So it fits that form. Oops, equals 0. And so that means that x is going to be equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So x is going to be negative b plus or minus the square root of b squared minus 4 times something all over 2 times something. Let's plug them in. So this becomes a 4 there and a 4 there. And then the a is a 1. And the c is a 5. So this becomes x equals to negative 4 plus or minus the square root of 16 minus 20 all over 2. So x equals to negative 4 plus or minus the square root of negative 4 all over 2. So now I want to deal with this minus in here. We have a negative inside a square root, so let's deal with it by pulling it out as an imaginary. So negative 4 plus or minus I root 4 all over 2. And so now square root of 4 is a 2, so this becomes minus 4 plus or minus I times 2 all over 2. And then we can separate this into negative 4 divided by 2 plus or minus 2i divided by 2. The 2's cancel. The 2 goes into 4 2 times. And so we get a couple final answers of negative 2 plus or minus I. Let's check our work. Does that work? Is that the value that makes that a true statement? So check. We have blank squared plus 4 times blank plus 5 should be equal to 0. And let's check one of them. Let's check the -2 plus I. -2 plus I. -2 plus I. Is this a valid answer? X equals to -2 plus I. Okay, so when I FOIL this, I'll end up with +4 minus 2I minus 2I plus I squared. When I distribute these, I'll get a negative 8 plus 4I plus 5. So I get a 4 minus 4I plus a -1. I squared is -1. Minus 8 plus 4I plus 5. So plus 4I minus 4I, these guys easily cancel. And then I get 4 minus 1, that's going to be a 3. So I end up with 4 minus 1 minus 8 plus 5. And that's going to be equal to 9 minus 9. That's equal to 0. Yep, that works out. Okay, so now let's check the other one. Check the other case where x equals to -2 minus I. So again, we have something squared plus 4 times something plus 5. And does that equal to 0? Hopefully it does. So we have -2 minus I minus 2 minus I. When we FOIL this one, we'll get -2 times -2, so that's going to be +4. And then we get -2 times -I becomes +2I. And then -2 times -2, we get another +2I. And then we end up with a plus I squared. Distributing, we get a -8 minus 4I plus 5. So then combining like terms, we get 4 plus 4I plus -1. Let's go ahead and rewrite that guy as a -1. -1. Minus 8 minus 4I plus 5. So plus 4I minus 4I, these guys cancel. Minus 4I plus 4I. And so what survives is a 4 from here, and then a -1, and then a -8, and then a +5, which still gives us 0. So works out again. Okay, so both solutions worked. Right? Remember that this notation of a plus and a minus means that there are two solutions. One of them is the one that has a plus in there, and the other one is the one that has a minus in there. So this solution and this solution is really a shorthand notation. This is a shorthand notation of both those solutions, and they both worked out. Okay, so this is what the author did. Again, went right over to the quadratic formula, plugged and chugged everything in there. We have the two answers, -2 plus or minus I, and then you can check it to make sure it works. Note that if the quadratic equation with real coefficients has complex solutions, then these solutions are complex conjugates of each other, right? So it's just another pattern that is noticed. When we are dealing with the quadratic formula, right, we're going to end up with a plus or minus. And if this ends up being a negative, we're going to end up with an imaginary, plus or minus an imaginary of a constant. So either way, we notice that we're always going to end up with a case like this, where if if the imaginary part of the complex answer is not 0, right? If this isn't square root of 0 here, this is not a 0, then we'll end up with two solutions which are complex conjugates of each other, right? So they always come in pairs is what we want to come out of this. If we have a quadratic formula and we know that there are complex number solutions to it, right? There are imaginary number solutions to that quadratic formula, that those solutions come in pairs and they're conjugate pairs of each other. Complex conjugates of each other. Right? Another way of saying that is, another way we're going to use that is that if we know that there is some equation, 3x squared plus, bx plus, 19, and that equals to 0, right? Some number goes in there. And we know, say we're given that we know that 3 plus 2i is a solution. Well, this is telling me that they come in conjugate pairs. So if this is a solution, this is telling me that 3 minus 2i must also be a solution. We'll use that down the road in this class. But that's what this is saying. They come in pairs, conjugate pairs. Okay, that should be everything and all you ever need to know to be able to do the homework in this section. As usual, let me know if you have any questions.